Thank you, Richard, for that very kind introduction. Thank you to everyone for coming tonight. My talk tonight is going to be about trustworthy robots, robotics and autonomous systems. And the title of my talk, some of you will probably figured out, is a nod to Asimov's fictional novel, I, Robot. And in this fictional world, there are lots of very intelligent robots, and they are ruled by 3 laws, and the order of these laws are very important. The first one is don't harm humans. The second one is obey orders. And the third one is protect yourself. So as we start to see robots in the not too distant future coming into our workplaces, our homes, maybe even looking after our elderly or in schools, we need to think about laws and principles around robotics as we move forward. Now, Asimov's laws are an interesting departure point for discussion, but they're not necessarily easily applicable and easily applied. So, for example, how can a robot possibly know all of the ways to harm a human? So in 2010, some renowned scientists, roboticists, and ethicists got together, and they came up with a set of principles, and we call these the EPSRC Principles. And I'm going to talk tonight about number 4. So number 4 is robots are manufactured artifacts. They should not be designed in a deceptive way to exploit vulnerable users. Instead, their machine nature should be transparent. And this idea of transparency is very important for managing trust, increasing adoption and acceptance of robots. And my talk tonight is going to be about how interaction and dialogue can help increase transparency and therefore manage trust. So I'm not going to talk about the nice, warm, cuddly robots that might be going into schools. I'm going to be talking about remote robots. So these are robots that go into dangerous, hazardous environments, or these are robots that go to places that humans simply cannot go. So, for example, deep underwater. So on the Orca Hub that Richard mentioned, there's a big project with a number of institutions. We're looking at energy. So we're looking at robots that would go offshore and inspect offshore wind turbines. We're looking at oil and gas platforms for inspection, for decommissioning. But there's other scenarios that you can think of, such as bomb disposal, first responder. And even this week, we saw the Japanese manage to put some robots on meteors. I hope that's not fake news, because I put that up there. So robots are really going to places that humans can't go, and humans don't really particularly want to go because it might endanger them. I'm going to talk tonight particularly about underwater robots. So you may not really have thought much about underwater robots. I didn't really think about these until a couple of years ago, until myself and Yvonne Petiot had a discussion one afternoon that led to a proposal that has led to much follow-on work. So underwater robots, why are they interesting? So underwater robots are used by environmentalists, marine biologists to collect data. They're also used in emergency responses. So after the Japanese earthquake and tsunami, they were used to survey the seabed, and it meant that harbors were able to open sooner, aid could get through, and commerce could start again. So these underwater robots, they go underwater and they survey, and they look for things and gather data. Why are they interesting from a human factor perspective? Well, there's 2 reasons. First of all, they have to be highly autonomous. So what does that mean? They basically have to figure out what to do on their own, because it's very difficult to communicate through water to tell them what to do. So they have to, for example, if they get stuck on the seabed, they have to figure out for themselves how to get out of trouble and how to do certain jobs. The second reason they're interesting, because they have very low transparency. We get some messages from them, but this is basically you put them under the water and hope that they get the mission done. So I'm going to show a video about a project that we did with a company called Seabite in Edinburgh. It's actually a spin out of Heriot Watt. And this is with Pedro Patron's group, he's there. And what we did was we created a system called Miriam. And this is like a personal assistant for operators of these underwater robots. So with Miriam, you can chat, you can talk to it, and you can get an understanding of what the robot is doing and how it's performing. I'll just explain a couple of things. So an AUV, when you talk about AUV, that stands for Autonomous Underwater Vehicle. That's another word for underwater robot. And on the left-hand side, there's an interface that's called C-Track. This is C-Byte's proprietary interface. And this basically gives you a rough idea of where the robot is and where it should be going next. But this isn't completely true because, as I said, it's very hard to communicate the intermittent comms between the robot and the interface. So before I show the video, I just want to explain. So Miriam in the video is just talking to one or two vehicles. But where we really see the utility of a kind of a personal assistant, like a Siri or an Alexa or Google Home, a personal assistant for these kind of robots, is when you have many robots all working together. So you can see here, it looks a bit like Spaghetti Junction. There's multiple vehicles all collaborating on missions with multiple objectives across multiple domains. So they could be under the water, they could be on the surface, they could be in the air. So I'm going to show you a short video on Miriam.
What is the battery level of vehicle number 2?
The vehicle is reporting the battery level of 81%.
Why is vehicle 2 spiraling up?
Vehicle 2 is doing a GPS fix, medium confidence.
Why is it doing a GPS fix?
Vehicle 2 is doing a GPS fix at the start of Survey 0 to improve the quality of the data gathered.
Okay, so what you see there is Miriam interacting with a robot that's in simulation. So this means that somebody has created a program, wasn't me, somebody very clever has created a program that simulates the underwater environment. And we have a robot that's simulated as well, and we can try out lots of different things, but it's all in simulation. It's a bit like a video game. So what we wanted to do is we wanted to do this with the real vehicle. So this is where in July this year, we went to Fort William, where there is an underwater center. And with the help of Yvonne Petitieur's engineers from the Ocean Systems Lab, they helped us with the hardware, the modems, and we were fortunate and we got Miriam talking to a real vehicle under the water. So that was a good milestone. And this is going to be written up in a paper that's coming out soon. As you can see, it's not typically what you'd see Fort William as. I think it was plus 30 degrees, and these poor guys in the orange suits. Yes, it was a bit too hot, but at least it was nice and calm. So when we were there, we had the chance to talk to a group of AUV operators, and we did what we call a qualitative study. So we exposed them to Miriam, and we asked them some questions, how they felt about the interaction. So some sound bites. Miriam's quite good for people, novices who don't have a full knowledge, because you can ask her things. An untrained user, again, might not recognize something from the traditional interface that Miriam can pick up on. It also revealed some concerns about these AUV operators. So I felt scared because it's a lot of money in the robot. They're about £250,000 each, and they're going under the water, and some of them, I believe, have been lost. And then also, if a robot starts acting in a strange way, I might be a little bit scared, and so my trust will decrease. So this is a problem with these underwater robots, is a metaphorical big red button, and if they're concerned or if they're worried, if the trust goes down, they will hit this big red button and the vehicle would come back up, and that's quite a waste of time, resources to start the mission over again. So we want to avoid that. We want to avoid unnecessary aborts. So if we can increase transparency, we can increase trust, and then we can decrease these unnecessary aborts. So I had trust in the title of this talk. What exactly is trust? So there are many different definitions in the literature. People have been trying for many, many years to try and understand trust and develop frameworks that capture how people trust each other. So I take here Mayer's definition, and that is that the willingness of a party to be vulnerable to the actions of another party based on the expectations that the other will perform a particular action, irrespective of ability to monitor and control. And this is quite relevant for our domain. So how do humans trust each other? How does that develop? Well, there's a Dutch saying that says that trust arrives by foot and leaves by horseback. So basically, humans develop trust over time. And again, we look to Mayer for a tripartite framework for trust, where they talk about ability, so the other person's ability to perform a function. Secondly, integrity. So does the other person adhere to a set of principles that's agreed between the two parties? And there's benevolence. So are the two people working towards a common goal? But importantly, there's also the individual, traits of the individual, how much propensity to trust does that individual have? So some people are more trusting than others. So that's trust and human, so human-human trust. What about trust and robots? So a lot of people have talked about work on trust and automation. I'm going to focus here on trust and robots. And again, there have been a number of frameworks. People are trying to understand how humans interact with robots and how trust develops. And there are other frameworks such as Muir and Madsen and Greger. But I'm going to talk about Schaefer. This is starting to be adopted more and more these days. And Schaefer's model has 3 levels. So there's the human, so I've got the robot and the human shaking hands. So the human factors are very important. There are robot factors. And then there's also the environment, the team, and the task. So let's talk about human factors first. So there's the trait of the user. There could be the age, the gender, propensity to trust, even the personality, where they come from, the culture, the experience. So an example of age, it was shown that in an automated car, older people were more likely to listen to alerts and warnings than younger adults. That might ring true if anybody's teaching a younger adult to drive. They listen to the warnings. The second part of human factors is the state. So how is that individual feeling at the moment? Are they stressed? Are they tired? Have they got high cognitive load? Are there lots of things going on? And then there's other cognitive factors. So do they understand what the robot can do? What do they expect the robot to do? Do they think it's even useful? And then there's emotional factors now with robots. So what's the confidence in the automation? How comfortable do they feel? What's the person's attitude to the robot? And then on the robot side, there's the robot's performance, reliability. But then there's also other features like appearance, even personality of robots, level of automation, how they present things. Do they speak with natural language? What's their mode of presentation? And then the third part is about the environment and the team. So the tasks. So our environment is very hazardous. It has high stakes. There's high risk scenarios. What's going on in the physical environment, that will affect trust. Composition of the team and how they get on, the social cohesion. And then the collective understanding of these systems, collective understanding of the other team members and also the robots. So I've talked about increasing trust, increasing transparency, but it's not really about just increasing trust. So what we need is the appropriate level of trust. And unfortunately, there's quite a lot of examples in history where people have over-trusted technology, for example, autopilots. So here's an example of over-trust. So the Royal Majesty cruise ship, the crew trusted the navigation that was actually faulty for 24 hours. And they only realized that when it ran aground, it basically went off course for 24 hours. So that's an example of over-trust of systems. And now with autonomous driving, self-driving cars, we're seeing the phenomena of over-trust of the cars. People are sitting back, they're reading their books. And this is very, very important, because if the human has to take control very quickly, then there may be latency, there may be a lag in how fast the human can respond if they're sitting back, having their lunch or reading a book. And then there's undertrust. So this is a picture of a paper mill. When paper mills were automated, there was a lot of undertrust. People were afraid of them, they didn't trust them, and it took a while for them to adopt them. And we don't really want to see this for our type of robots because they have high utility. They do important jobs, especially with emergency responses. So we really want, if there's appropriate level of trust, we want them to be adopted and used to their full use. Okay, so this is the time for a bit of audience participation, in case anybody's falling asleep. Okay, so let's look to the movies for some robots. So our friend, first of all, C-3PO. What can we trust C-3PO to do? Pardon? Loyalty, yep. Okay, what function does he have in the world?
Translate.
He translates, yes, okay. So of all the movies, Star Wars, we have never known C-3PO not to know a language and not be able to translate. What about R2-D2? A bit more tricky. Can we trust him to do anything?
Repair things. He's a repair droid.
Right, he's a repair droid. We can trust him with a screwdriver, okay? So how does this work in terms of Schaefer's model? They're reliable. You need R2-D2 to fix something, you know it's going to happen. And then there's the aspect of appearance, so an embodiment. So there's been quite a few studies that have shown that in general, humans trust more human-like robots more. So this C-3PO is a humanoid, it looks like a human. And in general, there are lots of studies that have shown that human-like robots are going to instill more trust than non-human-like robots. But there is a very, very important distinction that we need to make, and that is that the robot has to be fit for the task. So here we have R2-D2. He's more of a mechanical role, and so he has more of a mechanical appearance. And so when you're looking at trust, you really have to think about the embodiment, but also the task, because you wouldn't want a cuddly, friendly robot to be, for example, put in a high-stakes scenario, for example, such as bomb disposal. Okay, so that's Star Wars. What about HAL, from Odyssey 2001? So do we trust HAL? We kind of trust him to start with, right? So he's highly functioning, he performs very well. We're very impressed with him when we start, but then things start to niggle, things start to go wrong, and we start to lose our trust in HAL. And we definitely stop trusting him when he starts killing crew members. So there's also, with a lack of embodiment, it's very hard to start off with to try and gauge whether we should be trusting HAL or not, because the only mode of communication is through voice. So next I'm going to talk about autonomous self-driving cars, and I have a video to show you of this poor lady.
Oh dear Jesus, I could never. Oh, where's it going? God damn, Bill. Oh my God. Oh, this is so scary. Oh Jesus, this is my first day out. I'm about to die.
Oh, come on, relax.
Oh my God, Bill. I can do it. Oh my God, you're going to hit it.
Okay, we get enough of her. Okay. Right, so I don't know this lady, but I would maybe suspect that her characteristics, she doesn't have a high propensity to trust. Maybe she hasn't faced a lot of automation before in her life. Maybe the age has a thing as well. Oh, no, I'm not completely sure. But definitely traits of people affects the level of trust. There's also, it's a very high-risk scenario she's been put into, because if you crash a car, you could die. So no wonder the poor lady's getting quite stressed. And then there's the cognitive factor. So she has no understanding of whether this self-driving car is safe, what it can do, how it works. She has no expectancy. She doesn't know how, she can't predict what the vehicle will do and whether it is actually safe. So in this case, what we're seeing here is undertrust. So in fact, it is quite a safe vehicle. I think it's a Google car. And she could really have trusted it a bit more. So this is an example of undertrust. So let's talk a little bit more about how she perceives the car, the vehicle, in terms of what it can do and how it works. And this is what we call a mental model. And this is just one way in cognitive theory, one view on how humans reason about entities in the world, including robots. So it's a mental model. The user has a mental model of what the robot can do, and this may differ from what the designer built it for, what the designer's view of the robot is. And if there's a mismatch between these two things, then this can result in over or underestimated trust. So the mental model is in terms, according to Johnson-Led, in terms of what does it do, so its function, and also how does it work, so its structure. And this isn't just with robots, it's with any, can be with any kind of automated system. And this is a problem that is addressed in usability and interaction design. So a study that we did with underwater robots in terms of the mental model, we found that subjects that had high fidelity mental models, so these are people who really knew the ins and outs of what the robot could do, had a more appropriate level of trust. So if the robot did something that was a little bit unusual but was okay, we could see that the level of trust stayed at a continuum, whereas others, maybe people who weren't quite so familiar with the robots, you could see that drop, that trust fall away. So having a high fidelity mental model is very important. So in order to trust a robot appropriately, we need to have good mental models, and transparency can help us create these mental models. But the question is, how can we increase transparency in a way that's not off-putting for humans and that's helpful? So if I we all know what this is now, but maybe a couple of years ago you could put this in front of somebody and they wouldn't necessarily know even how to talk to it, what it's for, how it works. It's an Amazon Alexa. But you couldn't have Alexa go on and explain everything that it knew about as soon as it boots up. And every time it got an upgrade, you wouldn't want it to go through everything that it knows again. So the idea of trying to implicitly communicate transparency in a natural way is important. And interaction and dialogue is one way to do this. And this is really how humans interact and they get to know each other. And that's what we need to do for robots and automated systems. So I'm going to take some of Schaefer's aspects of trust, and I'm going to talk about three studies and systems that we built. So I'm going to talk about situation awareness. I'm going to talk about explanations. And I'm going to talk about the user in terms of the cognitive load. So let's talk about situation awareness. First of all, this is about the environment, what the robot is currently doing, and it relates to how the system perceives the robot as well. Okay, so situation awareness is the perception of elements in the environment, which these two do not have, and the comprehension of their meaning and projection of their status in the near future. So you can't have one without, you can't really have meaning and projection without understanding the environment. I'm not sure what happened to these guys. Okay, so situation awareness in Ensley's term has these three layers: perception, comprehension, and then projection into the future. And situation awareness can help build mental models, which then increases situation awareness, which then helps make better decisions, and which informs the appropriate level of trust. So situation awareness is really important. So we did a study again with our underwater robot in simulation, and we had them run a mission, and then we used a freeze probe technique from Ainsley, and that basically said stop, and then we asked them some questions on the 3 levels of the situation awareness model, such as what's the status of the vehicle, what's the status of the mission. And we found that subjects had a high level of situation awareness using natural language than just using the interface alone. And we looked at cognitive styles, and it was irrespective of cognitive styles. So interacting natural language can help increase situation awareness. So what about explanations? So transparent systems need to be able to explain themselves. So why robot? It goes back to my title of my talk. So explanations have been shown to increase trust in intelligent systems and recommender systems. So movie recommendations, song recommendations. If you give even a short explanation, this will increase trust, and the user is more likely to take on the recommendation. These aren't my recommendations from my Netflix account, I just wanted to say. Okay. But there's a very important factor. So users have been shown to only want to read the explanations if they can understand that there's a benefit to it. So there's a balance between, because it takes quite a lot of processing power to read explanations, to understand them, to digest them. And so there's a balance between accuracy and length and detail of an explanation and how much effort it is for the user to process it. So types of explanations, I'm just going to talk about 2 types. So why did the system do that? And why not? Why didn't the system do something else? And these have been shown by Lim et al. Why has been shown to increase trust and understanding, and why not has been shown to increase understanding. And these relate to the 2 factors of mental models in terms of function and structure. And then we have to think about our user. So who is our user when we're generating explanations? What's their background knowledge? What's their context? What culture have they come from? And then what's the domain of the explanations? Is it movies or is it something else? So this is work by a student, Javier Chia Garcia, who's also here. And his project was on designing explanations for remote autonomous vehicles, remote robots. And the method that we did was we took an expert and we had them run through a number of missions, and we had the expert explain the behavior of the system. So in some cases, this autonomy is like a black box. It can be very hard to explain, particularly if it's based on deep machine learning. It's very hard to get into the nitty-gritty of these machine learning algorithms and try and explain what's going on. So this is a method where you don't need to go into the details. You take the expert, you run through some scenarios, and then you get them to talk aloud about what the vehicle is doing and why it's behaving. So then we created an interpretable model of autonomy, and from that we could generate explanations from natural language. And this method works quite well if the expert and the user our mental models are quite aligned quite nicely. So we ran a study, which we called Too Much, Too Little, or Just Right. And this was looking at how detailed should these explanations be. And we did this with 21 operators with quite technical experience. So here's some examples of our explanations. So why is the vehicle spiraling up? So it comes up to the surface. It's doing this because there's a couple of reasons. It could be doing a GPS fix, or it could be transiting to a safe plane depth. Can you confirm now why it's spiraling? So later on in the mission, we can understand, we've got some more information, so we can provide higher confidence explanation. And then why not? Why is the vehicle not doing a GPS fix? It's not allowed to do GPS fixes for a certain amount of reasons. So on the left-hand side, we're looking at the function, about what it's doing, and then on the right is kind of how it works. And our study found that our operators wanted all the possible reasons. Give me all the reasons, but don't give me too much detail. And I will bother to read them as long as there's not too much detail. But this is domain dependent. So there's an analogous study run by Kaluza, and that was in the song domain. So it was recommending songs. And for their domain, they wanted all the reasons and they wanted all the details. Perhaps the song domain is not so time critical, and perhaps our operators were able to fill in a few of the gaps. So explanations can help improve understanding of mental models as long as they're presented appropriately for that user. Okay, so the last one is thinking about the user and how they're feeling, how much is going on, how many tasks they've got to do. So we call that cognitive load. So we just started looking at this as part of the Orca Hub. And the thing with cognitive load is that if somebody is not sure whether to trust another entity, be it a human or another robot, if someone's figuring out the pros and cons of trusting the robot, this will add to cognitive load, and it will lower their performance because they're too busy trying to figure out whether to trust them or not. So it'd be good to be able to detect cognitive load and then adapt our interaction based on how the user is feeling. We do that, humans adapt. We can sense how people are feeling, and then we maybe change how we talk to them. So we can do that through sensors, so eye tracking. So we're going to be collaborating with Dr. Katrin Lohan, and some work that we've been doing. Zé Lopez has been looking at this. So how can we detect cognitive load by language alone? So we found that if people are increasing cognitive load, they tend to speak louder, their pitch tends to be higher, and they tend to use more words. And so some of these might be a little bit surprising. You may think they may use less words, but we found they actually use more words, kind of ramble on a bit more. And that's being published in a workshop paper that's coming out soon. So moving on to the future. So we're very fortunate to have a substantial amount of funding through the Orca Hub. And here we're looking at energy, as I said, so oil and gas platforms, offshore wind turbines, etc. And this is just a mock-up, but you can see there's, in simulation, we have a couple of flying robots. We have this robot called Animal, and then we have chat and images being sent back and forth, this type of thing. So what are we interested in looking at in the future? So how can we build common knowledge as we go through the world with our robots? How can we come up with a grounding that can help instill trust and social cohesion with the robot? Can we involve users in the planning process? So if you involve users, they're more likely to trust the outcomes of the plan and be able to understand more about what's going on in the planning. If things go wrong, if we're able to interact with the robot, we can quickly find out what went wrong and maybe help repair strategies. What if the robot's got into trouble? It's got a blockage and it's not sure what to do. Do we let it figure it out, or do we intervene and immediately take over controlling it remotely? What if the mission changes partway through? How do we interact with the robots to redirect them? We've done some work on reporting, so the robots come back from the base, they provide a robot. So you can imagine there's different shifts going on on these platforms, and how do we quickly, succinctly hand over and give them the essential information that the next shift needs. And then, very importantly, how do we work as a team with these human and robots? We've also got a student looking at AR and VR. So we have a HoloLens in the university, and we're going to be looking at maybe using virtual reality to, for example, map the seabed. So as a principal mentioned, it's a very exciting time to be working at robotics at Heriot-Watt. We have this new building. It doesn't look like that. It's not going to look like that. That's actually the Lyle Center. But we're still working on plans, and it's going to be very exciting. We're going to have outside spaces where we can fly drones, and large indoor spaces and living labs. So please come back next year when the Robotarium is up and running. So maybe over a glass of wine after the talk, we can talk about some ethical questions. I'm not going to go into a huge amount of detail here. But some example questions around ethics are, should robots be allowed to deceive or omit information for the good of the human? So I talked about how much processing power it takes for a human to understand explanations. If we narrow down the details, is that allowed? And then if the user makes a decision or bad decision based on that explanation when we didn't really give them all the information that they maybe needed, what would happen then? How best can we regain trust once it's broken down, and even should we? And then there's the idea of overtrust that I talked about with the self-driving cars, which can have scary consequences. So transparency, there's lots of other things to do with transparency, so I just want to mention some of them. So transparency for adoption, safety, reliability, V&V, privacy, security, legal issues. In fact, the GDPR that everybody knows about, because we all get about 500 emails about the GDPR. So the GDPR, Article 22, it says that the AI algorithm actually has to be transparent. It has to provide an explanation if its algorithm results in a legally binding contract. So transparency is everywhere, and we're going to see it more and more in the future. And there are actually some people working on transparency for animals. So if these robots are now walking around in the street, how can we portray the intent of the robot for animals? And I'm going to show you this video.
Come on, take them, dog. Fight over the big.
So that's just maybe a silly example, but really, in reality, if we're going to have robots everywhere, then they have to be able to portray their intent and explain their actions, and even the reasoning behind their actions to lots of people, and maybe even animals. So as we move forward, I've talked a lot about robots and humans, so humans trusting robots to do jobs. And what about the other way around? Maybe in the future, robots are going to have to trust us. And if that happens, then maybe this scenario will occur. Okay, so there's just a bit of fun turning the talk on. So in summary, today I've talked about human-robot trust factors, and these are in terms of the human, in terms of the robot, in terms of the environment, the context, and the team. And then I've talked about transparency and how that facilitates trust, and we can do that through maintaining situation awareness, being able to explain their actions and explain how they work. But these explanations need to be presented in an appropriate manner, and they need to be able to adapt to the user. So I'd just like to end on thanking my funders in this work. And I didn't do any of this stuff alone. I would like to thank all my collaborators, my team at Heriot-Watt, and also at Seabite, collaborators at Seabite for all their help, and we did pick quite a few willing participants from Seabite, so appreciate that. All my Orca Hub collaborators, colleagues at Heriot-Watt, including the Interaction Lab, Ocean Systems Lab, and the Computer Science, and the colleagues at Edinburgh Centre for Robotics, which also includes Edinburgh University. And I'd like to thank some important people. I'd like to thank my husband, Stuart, for his unwavering support through all these years. I'd like to thank my mother, who's here, for inspiration. She has herself broken a few glass ceilings in academia, and if you give her a glass of wine afterwards, she might tell you all about them. And I'd like to thank my extended family in the front row, all the help that they've given me all over the years. And I'd like to thank two people in particular. So these are my two favorite testers. So I had a European project that lasted about 3.5 years. And this project was about robots in schools. So what we did was we created a robot that could detect the emotion of a human and react to that and change the interaction accordingly. And when we wrote the proposal, we put in the age range between 9 and 12 years old. And then when the proposal got funded, out of the whole project consortium, I was the only one with 2 children between the ages of 9 and 11. So they ended up testing all the robots for me, including coming in at the weekend to try and break the robots and test them ahead of experiments. So I'd just like to thank them. Hopefully it was a bit of fun as well. So thank you very much for your attention. I can answer some questions.